Our first invited talk this morning is Stéphane Mallat. He received his PhD from the University of Pennsylvania in 1988, after which he became a professor at the Cron Institute. In 1995, he became a professor of applied mathematics at École Polytechnique, and since 2017, he holds the data sciences chair at the Collège de France and École Normale Supérieure. He is known for fundamental contributions to wavelet theory and multi-resolution analysis, signal processing, and recently for his construction of the scattering transform, which provides a profound connection between multi-resolution analysis and deep learning. He has many awards. Just among them, he's a member of the French Academy of Sciences, was a plenary lecturer at the International Congress of Mathematics, and a 2007 EADS Grant Prize of the French Academy of Sciences. Let us welcome Stéphane Mallat. Today he will discuss harmonic analysis for high dimensional learning and deep nets.
Well, thanks very much, Rachel. And I'd like to thank you and Jen Fenglu for the organization of this conference, because I do think it's very important nowadays to build up a mathematical community around these problems. So trying to pose a little bit the problems which are behind in mathematical terms. So that may look a bit naive, but if you consider problems in high dimension, whether it's classification, for example, you want to label an image Y given 1 million pixels, or whether it's a regression problem like the ones that were a bit presented by Roberto Carr yesterday, for example, computing the energy of a physical system described by X, which is a high dimensional vector. The way to pose the problem for supervised learning is already a choice on how you model this problem. And to try to see that, I would like to begin with a naive question, which is to wonder whether it's more difficult to estimate this label Y from X when D increases. So of course, this is a completely ill-posed problem, but the way you're going to take this problem and make it well-posed is already a choice in mathematical terms. So if you take a deterministic point of view on this problem, which is a little bit the point of view that Wayne E. took yesterday in his very beautiful lecture, then you'll consider that the problem is about a function approximation problem. You want to find the function f of x, or approximate it, given some point which is given to you on this function x, on the different values of x. And now x is going to belong typically to a set omega of very high dimension of the order of omega. So it's obvious that when the dimension of the set omega increases, the number of potential function is going to increase exponentially with the dimension. And here you're facing with the curse of dimensionality. Now, if you're working in functional analysis, if you think of this problem, yes, obviously, the problem is going to be more difficult when the dimension increases. Now, there are ways to deal with this difficulty is to observe that the function f is going to have some form of regularity. And this form of regularity, you can capture it with function spaces as the one that were described by Wayne and E. And then one way to approximate your function is to define a dictionary or a basis and then expand your approximation in your dictionary. And this is typically what you're going to do with a two-layer network, and you get approximation theorems. Good. But then you can take a different point of view, which is usually the point of view that is taken by engineers in this domain, and say, well, what you really would like to get is, as an answer, is the most probable Y given the observation X. Now, if you think in these terms, then if you have more information on X, then it should be easier to estimate Y. So if the dimension D of X increase, no, it should be easier to perform your point of view. But where this miracle probability distribution comes from. Where it comes from is a standard change of point of view on your function is, instead of looking at the value point per point, you can look at the level set of your function. So for a given y, your class omega y is really a level set of your function. And what you're really interested in now is in the geometry of this level set. So when you take this point of view, the problem becomes a geometrical problem to characterize these level sets. Now, how are you going to characterize such level set in very high dimension? Then you are in the world of probability. What you're going to do is to define a function phi, such that phi is going to concentrate your level sets, concentrate your level set in much smaller domains, which hopefully are going to be separated for different y. So where is the regularity appears? The regularity appears through your ability to concentrate these sets and to perform the separation. That's where mathematically regularity is going to come into. Now, what is phi of x? The interpretation in this framework is totally different. Phi of x in this framework are empirical moments. And if you apply a large deviation principle, you can get a model of your probability distribution. The log probability is going to be essentially linear as a function of phi of x. So here you have two totally different approaches to this problem. The left one, which is really where I've been working for most of my professional ones, especially being French, very Cartesians, is extremely effective if you are in low dimension. Regularity can be expressed, you have the Bezoff spaces, you have all kind of well-defined space, holder spaces. If you move in high dimension, the point is it doesn't work so well. The functional spaces are usually relatively crude to describe the problem because the prior information is on the geometry of the level set. And that's what I would like to insist on. If you take deep convolution networks, if you look at numerical experiments, many of them have been done. So let me remind you, have a cascade of convolution operator and linear operator along the channels, followed by nonlinear pointwise operation, which is in this case going to be a linear rectifier. And you cascade this operation with a subsampling. You are going to obtain ultimately a representation phi of x, which is of much lower dimension. And what people have been observing is that within this deep layer of your net, you see the concentrations of your different classes and you observe these separations. So the question is, how come, why does it work despite the curse of dimensionality? Because obviously you still face a curse of dimensionality. So somewhere the architecture incorporates the necessary information to capture this concentration function. And what I would like to look at here is to try to understand the prior information which is available and how is that related to this architecture. And more specifically, understand what's the specificity of the spatial convolution, but also the transformation along the channels and of the Relu. And there we're going to have essentially a harmonic analysis problem. At least you can view it from the point of view of harmonic analysis. So first, what I'm going to do is look at this problem without any learning to try to understand the nature of the prior in such a problem. And I'm going to begin with an apparently simpler problem, which is the modelization of non-Gaussian processes from one realization x0. And typically you'd like to model complex phenomena, which is still a very open problem in physics, such as turbulence. Here we're going to see how harmonic analysis comes in, wavelets, sparsity, phase, but also we'll see how it relates to classification. The point is, when you deal with very complex problems such as ImageNet, you need to learn, and the key question will be what's the mathematical nature of this learning, in particular along the channels. Okay, so I'm going to begin from this statistical physics point of view. So you would like to generate a random process given only one realization. I'm going to suppose that I have this function phi of x which concentrates, which essentially takes any typical realization and concentrate it in the neighborhood of the expected value of phi of x with high probability. Now then you can build a maximum entropy model, which means defining a probability distribution which has the same mean, but which is as regular as possible, namely which maximizes the entropy. And if you solve that problem, you immediately realize that the model is going to have a Gibbs distribution. In other words, the log probability is going to be linear as a function of the moments phi of x. Now, obviously, you are going to have an error. The error in this case you can verify is essentially the excess of entropy, because you have typically a model which is too regular. And the whole question in this problem is, how should you choose your function phi in order to get a good model? So the first simple idea is to say, okay, I have some prior information about x. I know it's stationary, so I know that P of x, the probability distribution, is invariant by translation. Simplest model you can build is use second order moments. So you compute an empirical covariance between the value of your process at a point u and u shifted by tau. And because you know that your probability distribution is invariant by translation, you can average in space. And if you have some prior which is stronger, you are going to have a concentration, because this is going to essentially here corresponds to some form of weak ergodicity. If that's the case, you compute your maximum entropy distribution, you get an exponential of bilinear form. This is a Gaussian model. So what did you do? You had a probability distribution. Essentially, you've been calculating the principal axis of your probability distribution. You've defined the most regular distribution, which is Gaussian here. And here are the examples. This is a fluid dynamic turbulent. This is the Gaussian model, same second order moments. And obviously, you don't capture geometric structure. This is another gas which is turbulent. That's the Gaussian model. Okay, so how can you see the error? You see the error by picking a well-chosen direction, omega, and looking at the true distribution along omega and compare it with your model, which is Gaussian. And if, for example, you have some form of sparsity, you're going to have a very peak distribution. So obviously, your model was wrong. So where is harmonic analysis coming in? Well, because your distribution is invariant to translation, the principal axis is the Fourier basis. So how are you going to choose omega? You're going to choose it relatively to the Fourier basis. And here you are in harmonic analysis. Okay, so in this case, if you want to have a sparse representation, comes in wavelets. Suppose most of you know about it. You have a localized function. Here I have two wavelets with two different phase corresponding to a cosine and a sine. I can view it as a complex function. I rotate my wavelets as a sine wave. I dilate it, and I have a whole family of wavelets with different phase. So the wavelet transform in this case is just a convolution with each of these wavelets. And in the Fourier domain, it's therefore a product with a function which has a localized Fourier support. If you rotate your wavelet, you'll get different frequency bands, dilated, different dilated frequency bands. Good. Now, if you look at the wavelet coefficients at different scale, one very important element is that they are going to be totally non-correlated because they live in different frequency bands, and frequencies decorrelate stationary processes. So let's look at an example. This is an image. These are the wavelet coefficients. Good, they are sparse. So obviously you've captured something that your Gaussian model didn't give at you. But if you look at different scale, they are still sparse, but you can immediately realize that they are very strongly dependent. But the coefficients are totally decorrelated. Why? Because of phase fluctuations. So the next problem is, if you consider all these images as being your channels, is going to be to capture the dependence across the channel, in other words, across scales and angles. And that's where the rectifier has a very important role. The rectifier, you can view it in harmonic analysis as a phase window. So why? I'm going to have wavelets which has potentially different phase. If I look at a real wavelets, I obtain by multiplying it by a phase term. And that's the work of Sixin Zhang and Gaspar Rocha. Now, if you apply a rectifier on that, it's like applying the rectifier on the real part of your complex valued function. But the complex coefficients, I can separate the modulus and the phase. The Relu is a homogeneous operator. So the modulus, I can take it outside. And what do I get? I get a function of the phase. And if you look at this function of the phase, it's a window on the phase. It's a window on the phase which is translated by the alpha, which is a specific phase of the wavelet. So what you're doing, you are looking at a windowing of your wavelet coefficients, and the windowing is produced by your rectifier. And this is going to create the correlation across scales and angles by specifying phase alignments. If you look at the original problem, instead of doing a correlation of the original wavelet coefficients, let's take all the channels which are now transformed by your rectifiers, and suddenly you have correlated coefficients which are capturing interactions between scales and angles. You have a Gibbs distribution, you can sample this Gibbs distribution, and that's what you get. Suddenly, you get realization which do capture the geometry of the problem. The essential reason here is that you've been able to realign the phase, which is restoring all these coherent structure. Now, in this case, the problem is solved without learning at all your concentration function because you have enough prior information, scale separation, you know about phase and so on. Okay, you can now apply that to classification. So for classification, what you would like is to capture each of the class Y by hopefully approximating your log probability distribution. What do you know? Essentially, if you translate your image, it's not going to change the class. So very often you have a problem which is stationary. So you will be able to construct phi by averaging. And if you again have some weak ergodicity, you'll get some concentration. You also know that your problem is usually stable to deformation. If you have, for example, here a digit here, 3, which is slightly deformed, it's still a 3. So your level set is invariant to a small diffeomorphism. In physics problem, it's going to change a bit with diffeomorphism, but regularly. So you want this regularity to diffeomorphism. Last thing, if you don't learn phi, you'd better preserve as much information as possible. So how can you do it? If you take your X and you first want to concentrate its value by averaging, you are going to do potentially a local average with your kernel, let's say a Gaussian kernel. And the result of that is obviously you are going to lose a lot of information. So the whole game will be try to get a function which concentrates but preserve as much information as possible. Where can you get the information you've lost? Obviously, these are the high frequencies, the wavelet coefficient, but you cannot average them because they oscillate, so the average will be 0. Like previously, what you can do is apply a rectifier. If you apply a rectifier and you average, then you are going to get a new set of coefficients which are going to be informative about your random process and are going to depend upon the different scale orientations, potentially phase. Now you averaged, therefore you lost information. Where is the information lost? It's the high frequencies of this rectified function that you can again extract by applying the high frequency wavelets, which captures its variations. And again, you are going to get a new set of descriptors by again applying a rectifier against the new channels that you've created and an averaging. If you do that, you essentially have a neural network, which we call here a scattering transform. So you have your first wavelet transform and the average here. Each of these coefficients, and then you apply your rectifier, are then again average and you compute the wavelet coefficients. Each coefficients are again average and the wavelet coefficient and so on. So it's a cascade of wavelet transform rectifier, wavelet transform rectifier. It looks like a convolution network, but there is no connection across scales, and no learning of the filters. So how far can you go with that? So first question, what are the properties? One important property is stability to deformations. If your image is slightly deformed, then the scattering transform is just going to be transformed by an amount which is depending linearly on the size of the deformation. Now that's very important for classification. What you're going to do is take X, compute your coefficient, which is this scattering transform on a local grid here. And these are all the coefficients here along the channel corresponding to the different phase and angles. And then a simple classifier that you're going to learn, linear classifier. If you do that on simple problems such as digit recognition or texture recognition, where the source of variability comes from translation deformations, you get essentially the same performance than a deep net where you learn everything. If you work on problems where you have a lot of prior, such as physics, where you know about the invariance, stability to deformation, importance of interaction across scales, like the problem in quantum chemistry that Roberto Carr described yesterday, that's the work of Michael Eichenberg, Georgios Exkacharis, Michael Hearn, and Louis Thierry, then you can get regression of quantum energy with about the same precision than DeepNet, but until now, all the database corresponds to relatively small molecule. If you work on ImageNet, then the situation is totally different. Much more complex images, the error is about 40%, whereas if you learn, you get 20% error with a ResNet, even 7% error. So then the question is, what is low? If you think in functional analysis term, which has been for a long time the way of us thinking, then the idea is to say, okay, you need to capture regularity. Regularity, you're going to capture it with sparsity. It makes sense because that's about patterns. So you're going to take your transform, try to sparsify it in a dictionary, which is this idea of capturing patterns, which are the columns of the dictionary. And how can you do that? We all know that. You can cast it as an L1 optimization problem where you approximate your data from your dictionary with a sparse code, and you impose sparsity of the code with an L1 node. Now that kind of thing can be solved with iterative proximal algorithms. And what you can do is create a network which essentially embeds such an iterative proximal algorithm. Each layer is one iteration. That's the work of John Zarka, Louis Thierry, and Thomas Anglès. And you can use a smarter homotopic algorithm in order to reduce the number of iterations and the classifier. So here, if you learn, you are learning one matrix. You do several iterations, but there is just one dictionary, one threshold, which is the parameter of your optimization. And you want to minimize the classification loss. You do that with a stochastic gradient descent. You can verify that within about 12 layers with such a homotopic algorithm, you have convergence to a sparse code, and you can apply it to your problem. So AlexNet was 20% error, scattering transform alone with a simple classifier, well, double layer classifier, exactly the same than AlexNet, you have twice more error. And now, if you do a sparse coding is just along the channels, okay? No spatial convolution. You're going to get very sparse outputs, and the error drops. And that kind of drop, we were totally unable to get it before, 18%. We are slightly below AlexNet. So the question is why? The immediate reason that comes to mind is to say, okay, the reason is that I've detected patterns and classification should be based on patterns. So you can check that. How can you check it? Let's reconstruct from these patterns. Okay, I reconstruct an approximation of the input from the sparse code by reapplying my dictionary. So this is not sparse anymore. It's just basically very similar to the input up to some elements that I've removed because of the classification. And surprise, the error is the same, 19%. So it's not about sparse code because the sparse code has been destroyed by applying Z. So question, can we eliminate the whole sparse coding? So a naive way to do it would be to say, okay, let me scattering form. And let me make, again, just along the channel, a projection to a low-dimensional space. But this is a linear operator. I go in a low dimension. A linear operator is not going to change a linear classifier. The area is going to be the same. The only difference is that now I am in lower dimension in this intermediate point. So that doesn't work. That's the work of John Zarka. Let's do something else. I'm going to go in this low dimensional space. And now I'm going to think in terms of metric. I'm going to warp the matrix. And I'm going to warp the matrix with this operator. Essentially, it's about replacing the sparse coding by just a matrix multiplication multiplied by the rectifier. If you look at that, this operator, it's diagonal once you've applied the matrix D. The matrix D puts you in a higher dimensional space, typically from 5 to 10 times bigger dimension. Then you apply your diagonal operator, which can be a Relu, but it can just also be a sign function, which maps you to 1 or -1, which means that you have no sparsity, but a very interesting metric warping. Same thing, you learn the dictionary D, you get even better result, 18% error. Not at all about sparse coding. Now let's do something else. Instead of doing brutally the scattering transform and then afterwards the change of metric, let's do this change of metric like DeepNet do after each layer. So first you apply wavelets, so there is no learning on the spatial operator, and a rectifier. And then along each channel, you apply your change of metric operator, which first reduce dimension with a linear projector, and then does in this lower dimension, this warping with this diagonal operator after applying D. So each time you learn the projector and the matrix DJ here. Then you reapply wavelets at the next scale, standard wavelets, Relu, and you change, you do a warping, and you iterate. Finally, linear classifier. And the result, the precision increase, you essentially go to a ResNet precision. Here, there is only 6 layers, but within each layer here, you have a rectifier, so you can consider that as a 12-layer network, and you essentially get the same precision than a ResNet, so you're really getting to state-of-the-art. What does it mean? It means first that it seems you don't need to learn the spatial filters. The spatial filters are given to you by the mathematics and the prior. Wavelets are enough, you get your sparsity, you separate scale, which is very fundamental. What is really that you need to learn is what is going to happen across the channel if you have a problem as complex as LXNet. And there is a lot of very interesting mathematics to be done because these warping operator, diagonal warping operators, have very interesting property that depends upon the choice of your rectifier. So let me conclude on that. Let me go back first on this bias versus Descartes, which is a very cultural problem. Again, it's almost like saying France against Anglo-Saxons. In France, you have a tendency to make mathematics, and in the culture, I mean, when you think of what's the weather tomorrow, it's going to be rainy or sunny. It's not 20% chance of showers. Well, I must say, in the case of high dimensionality, I think Bayes is right. It is fundamentally a probabilistic problem because it is fundamentally a problem of measure theory. You want to understand the geometry, the property of your measures, and concentration tools are at the heart of that kind of problems. So I do very strongly think that it's more an issue of understanding the concentration properties of these measures than creating new functional space, but Wyman-E may prove me wrong, we'll see. Now the harmonic analysis side. I do think that it's at the core of the problem, very simply, and that's a thought that is shared by, I think, most of you, because Fourier transform is behind the invariance on any group, and in particular translation group. And here it allows us to understand the nature of these concentration tools. The difference with what we're used to do in harmonic analysis is that this is fundamentally nonlinear harmonic analysis. And phases, which we had a tendency to systematically eliminate with these thresholding operators, or by thinking of unconditional basis where you essentially eliminate all phase and signs. Here, phase plays a very important role, and rectifier is acting there. So in terms of space, scale separation is very important, and it looks like it may be enough to understand the nature of the spatial filters, even to get to state of the art. I think really the mystery, as I see it, is to understand this metric learning problems. Now, obviously, we need to simplify the problem. These architectures are too complex. And essentially, what I'm trying to say here is that it's possible to isolate much simpler diagonal metric warping operators. And in that framework, the issue would be try to understand what are the properties. You see, the concentration doesn't go through a continuous flow. It goes through 5, 6 steps in that case. So it looks like an multi-scale approximation scheme, but on the measures. What class of measures does it address, and so on? These are very open problems. And I'll finish there. Thanks.
Thank you, Stéphane, for the wonderful talk. We have about 10 minutes. I'm being told that Waynon has some first questions for you. So we're going to go ahead and let him start by asking you a question. Waynon, are you there?
So, okay. Anyway, first a comment about the remarks you made, the difference between Descartes and Bayes. I think there's no real conflict because in high dimensions, even if you want to think about function space in high dimensions, concentration measures is a very, very important aspect of it. As a matter of fact, my guess is that when we look at classification problems, the kind of objects we have to look at in order to define function space would be the kind of objects you looked at on your right column. It's not proof, but this is my hunch. So this is the first comment. Secondly, I want to ask you about, do you have a good idea how to define a good set of phi? You showed examples that some phis are bad, some are good. But in general, do you have a sort of a guiding principle how to define a good set of phis?
Okay, so I'm going to try to, thanks very much for this question, to the 2 points. The first point is, of course, I agree that there is an equivalence and correspondence between the two, but the hypothesis may be of different nature. If you think in stochastic terms, then you're going to look at problems such as independence, decorrelations, elements that are not coming naturally in the mathematics of functional analysis. Now, what is very interesting is that at the end of your seminar, in fact, you came back to a Monte Carlo approach where you said, okay, this integral, we're going to approximate it with a Monte Carlo integration. Now, in that sense, there you are indeed moving, and you're right, there is an equivalence. But here, one element which is a bit, and which is like appearing in your proof, is that the high dimension is along X, where we don't have multiple examples. So we have to understand really the nature of the random process and what are the independence elements. So I do have a tendency to think that the core mathematics is going to be a little bit different. In the same way that in image processing, when we were doing signal processing, I very strongly believe that in most problems, level set were not the right tools. When you are in 2 dimension and you work with level set in 2 dimension, you have very complex curve, and it's much easier to work with the function itself. Well, and then you are in functional analysis. So yes, there is an equivalence, but yet the math tools are not the same. Large deviation theory comes into it. All the work of Varadime is at the core of all this, which doesn't. Now, your second point, the short answer is no, I don't have the general principles, but we see that obviously symmetry plays a very important role and therefore harmonic analysis comes in. But I think that what is really new coming from all these deep nets are indeed the learning of these metrics warping. In other words, this transport of measures. But again, on transport of measures, people have a tendency to think as if it was a low dimensional problem, you can do a transport of measure, but that's very, very difficult in high dimension. So we need to understand what is the regularity which is below that allows us to do this transport of measure. It's not enough to say, I transport the measure into a Gaussian and there exists a solution. Yes, there exists a solution, but curse subdimensioning comes in. So I don't have the principle, but I think there is a lot of very interesting mathematics to be done. And a number of people obviously already doing it.
Renan, did you have anything else to say?
Yeah, I have to make a correction. Really, it's not at the end of my talk, it's the very beginning. You know, defining function space in high dimension begins with a representational function in expectations. It's not about the usual regularity. It's starting from the very beginning. You have to
right,
think about how to represent functions as expectations. That's the starting point.
You're right, sorry,
So
that's an important point. You're right, but well, it's to be thought. That will be a very interesting conversation to pursue.
Let's talk about this later offline.
Thank you. We have time for a couple more questions. Let's, in the chat, we have the question, why is d rho dt a metric warping? The output of Relu does not seem to be a metric.
Okay, the metric is going to be, okay, d rho dt, d transpose, is taking your vector in your low dimensional space and you come back in your space. So initially, you could have a metric on X, which is a Euclidean metric. And in this Euclidean metric, if you were doing the classification, you would get an error of the order of 40%. If then you apply a linear classifier on the output, which essentially only rely on the Euclidean metric, you get an error which is less than 20%. So what happened? What happened is that apparently the classes have been separated much better. In that sense, if you consider the Euclidean metric in the new space, you get a representation which is better separated. So the metric, it's like in kernels, okay? You can view d rho d transpose as an elementary kernel. And in the same way, a kernel defines a new metric in the kernel, in the feature space, as they call it. So it's in that sense that it's a change of metric.
Thank you. We have time for one more question. We have here, did you consider the distributional robustness of the structured model versus the ResNet? How does the structured architecture behave outside the ImageNet database?
Okay, for now we've just tested on the ImageNet, but you're right that there is a very interesting question about robustness here. If you begin to put such priors on the architecture, which is much stronger, for example, are you more resilient to adversarial examples? Now, the instabilities in adversarial examples comes from the fact that you have operators which are not bounded. The issue would then be to see whether you can control the norms of the underlying operators and so on. So we didn't do it. We are just right. When I say we, it's really John Zarka and now Florentin Gut working on that. The first experiments are being done and I'm giving you the results, but that's a very interesting line of research indeed.
Okay, and I'm just going to squeeze in a question here. I'm wondering if you can comment on the difference in computational cost or efficiency between your approach versus, say, the ResNet with 50 layers, what people do in industry.
Okay, if you take, for example, as I said, what we have is something that would be equivalent to a 12-layer network, because you have your spatial filtering and the 1-1 operation. The computational cost of executing the network is the same, because it's just about how many filters, their size, and so on. For the learning, we haven't checked whether you can learn a bit faster or not. That I don't know. ResNet are really quite efficient. The hope is that you can learn from fewer examples if you put more constraints. And one of the things is that, as I showed, you don't need to learn your metric warping on each layer. One metric warping is already enough to go to 20% error. If you go from 1 to 6, then you go from 20% error to 11% to 12% errors. But so you can adapt. You don't have to get and the fact that you know the filters in space is hopefully going to be useful to learn from fewer examples. But that has to be demonstrated.
Yeah, that's important. Okay, thank you, Professor Mallat.